Right. So the first section, 3.1 of this chapter, is on a formula of Euler and working in arithmetic modulo p times q, where p and q are primes, and in particular finding roots, as in the opposite of raising to a power, right? So the context for this entire section is an integer that we're going to call n equal to p times q. That is the product of two distinct primes p and q, which for cryptographic purposes they should be thought of as large primes. And what is crucial to this section, one of the central questions in this section, and what is crucial to RSA crypto system, is understanding the structure of the group of units UN. And that's what we're going to be discussing for the rest of this section. In order to begin understanding the structure of the units modulo n equals p times q, we start by recalling a fact, which is the fact that when you take the units modulo p, a single prime p, that group is cyclic. And when you restate this in terms of congruences, this is exactly the same as saying that there is a primitive root modulo p. In other words, a number, let's call it a, necessarily coprime to p, whose powers a squared, a cubed, all the way up to a to the p minus 1, which is actually congruent to 1 mod p, those p minus 1 distinct powers actually exhaust all of the elements of UP. Let me remind you that UP consists of p minus 1 elements. It's a group of order p minus 1. It's certainly abelian, but as I'm recalling, it's actually cyclic. And of course, this is closely connected and in fact implies very easily Fermat's little theorem, which is the assertion that any element of UP when raised to the power p minus 1 gives 1 in UP. In other words, you get a congruence a to the p minus 1 congruent to 1 mod p, which is one formulation of Fermat's little theorem when a is coprime to p. So the reason why the fact that UP is cyclic is strictly stronger than Fermat's little theorem is that if you just look at Fermat's little theorem, it leaves open the possibility that perhaps a smaller exponent that p minus 1 could possibly suffice in the statement of the theorem. However, another way of restating fact 1 is the statement that of all the exponents with the property that a to the L is congruent to 1 mod p for a coprime to p, the least positive one is actually p minus 1, that no smaller exponent actually satisfies this. All right, so the next step is talking a little bit about what happens when you move from modulo a prime p to modulo n, which is equal to p times q, the product of two different primes. And this is a one theorem of Euler, not a major theorem. Euler has many different theorems named after him. But this is the theorem in which we get this formula for the exponent of the group UN. In other words, what is the smallest positive exponent? Let's call that L, such that when you raise any element of UN, which corresponds to an integer coprime to n, an integer a coprime to n, arbitrary integer a coprime to n, right? What happens, how can you achieve that integer raised to the L be necessarily congruent to 1 modulo n? So what this nifty little formula of Euler says is that, as a matter of fact, the optimal L here is the least common multiple of p minus 1 and q minus 1, where p and q are the prime factors of n. In particular, of all the possible exponents, the smallest one is L, equal exactly to the LCM, least common multiple of p minus 1 and q minus 1. But of course, any multiple of this L also has the property. It's just so happens that this least common multiple is the smallest possessing it. Now, if you don't like a formula involving the least common multiple of two numbers, and you're a fan of greatest common divisors instead, let me remind you that the least common multiple of two numbers is equal to their product divided by their greatest common divisor. So in the theorem of Euler, we can take L equals to the product p minus 1 times q minus 1 divided by the GCD of p minus 1 and q minus 1, if you prefer. So next, again, with n equals to p times q, this claim number 2, it captures a little bit of what is happening in the group of units. So this claim says that when you raise elements that are units modulo n to two different exponents, provided those exponents are congruent modulo L, the least common multiple of p minus 1 and q minus 1, then the answers that you get are the same modulo n. And if you want to look at the details of the proof, they're written here on the slide. But in reality, all of this is a consequence of the fact that since every element A has order dividing L, simply because a to the L is equal to 1 always. So by Lagrange's theorem, the order of A is a divisor of L, and therefore the powers of A repeat with period equal to the order of A, and therefore, since L has to be a multiple of the order of A, in other words, the order of A is a divisor of L, So when the exponents are congruent modulo L, they are necessarily congruent modulo the order of A, and therefore the powers are the same in the group UN. So now we have this theorem about the possibility of taking roots in the group UN, right? So if x, an element, an integer x is congruent to the uth power of another element y, right? So x is congruent to y to u mod n. And if you're trying to solve for y in this equation, so in other words, if you're sort of trying to take the uth root of x to get y, then the correct notion of taking the uth root is, as you would expect, raising to the exponent 1 over u. But what it means to raise to the exponent 1 over u is actually taking the multiplicative inverse of u modulo L, which, remember that in this case, the group UN, the Lth power of any element is equal to 1. So the exponents, when you're taking powers in UN, are in some sense elements of Z mod L. And for that reason, the inverse operation of raising to the U is raising to the U inverse, where U inverse is the element V equal to the multiplicative inverse of U modulo L. Now here's some remarks after this theorem about taking roots in UPQ. So the first thing is that if the exponent, if you take the exponent u to be represented by a positive integer, and if you take v to be the multiplicative inverse of u modulo L, but also to be a positive integer, so if you are taking positive integers representing the elements of Z mod L, then the hypothesis that the elements x and y belong to the group UN is not necessary. In other words, this works for taking roots of any elements of the ring Z mod n. So this works for taking congruences modulo n, raising to a power, and the inverse operation, as long as you take exponents that are positive and multiplicative inverses modulo L. The condition that the exponents are coprime to L, that is essential. The condition that the base elements x and y are coprime to n is not essential, and in fact it is redundant. So a couple more remarks. The first one is that when the power that you raise to is not coprime to L, which is the order, I'm sorry, the exponent for the group UN, then the question of extracting roots, uth roots, is there's not a unique uth root. So the question, the problem is potentially more complicated. But an even more important remark is the fact that the operation of raising to a power is very efficient, provided you know what the power is, right? So in order to invert the operation of raising to the u, you need to raise to the multiplicative inverse of u modulo L. However, the determination of L depends on knowing the factors P and Q of n. So if all you know is that you're doing arithmetic modulo n, but you do not know the factorization of n as P times Q, then it is in fact unfeasible in general to even find L, and therefore it's not that undoing the operation of raising to the u by raising to the v equals u inverse is difficult. Is that the determination of the multiplicative inverse of u modulo L is itself difficult, and unfeasible if you do not know the prime factors p and q of n. This is critical to the security of RSA.